Okay, we're going to start with a week 10 material. This is about projective geometry. I'll start with a few motivating remarks. So let me just put section 5, projective geometry. We can probably start with the following observation in more sense than one. Let's imagine we're looking at some train tracks which are parallel, and let's imagine that we've got an eye that is observing these train tracks, and there'll be a pupil here. And what happens is that the light bounces off the train tracks, goes through the eye, through the pupil of the eye, and then gets drawn, if you like, onto the back of the retina. So let's imagine, for the sake of argument, that the retina here is just a line, for the sake of simplification. So a point here would have a light ray bounce off it through the pupil and hit the back of the retina somewhere here. And similarly, you would get a point appearing here. So let's just sort of label these with a plus. And then what happens if you take a point that's quite a long distance away? Then, and this is not going to be a very good line, but that'll do, you can see that you get a point that's kind of closer. And similarly at the back here, you get a point that's a bit closer, so we'll label those with minuses. So what appears to be happening then, from the point of view of the retina, is that as you take these parallel lines further and further, go further and further along them, they converge together. And if you imagine standing on some train tracks, that's exactly what happens. You see the tracks converging towards the horizon. And so if you take the sort of limit of this situation, then you'd get a sort of imaginary point right at the end here, which is the pointed infinity. So you can, again, thinking about standing on train tracks, you can see there is a distinct point in the distance that the lines appear to converge to. So just in this kind of very basic setup, you can see most of the features of projective geometry. So you can project, which means to sort of throw onto a plane to get an image, and you get points at infinity appearing on those in those different projections onto different planes. And the other thing that's absolutely crucial is that it doesn't matter. So the only thing that matters is which line you are in, not in terms of where it projects onto the back here. So not how far along it is. So any point here, or further along, if that were parallel, there will give you a point that's will contribute to the projection of the colour that appears at this point and intensity. And similarly for these lines here. So what we're going to do when studying projective geometry is to take affine n space and replace all of the treat all of the lines in affine n space through the origin as their own individual points. justified by this kind of setup. There are lots of good reasons for thinking about the geometry you get there. One that's relevant to this course is that it turns out that considered in projective geometry terms, there is no difference between any conic section. They are all the same. The only difference is how you're projecting, so which plane that you're projecting onto, that gives you the different versions of the same conic section. So we'll see later in projective geometry all conic sections are the same. And I thought I'd just very briefly mention another motivating idea. There is a particular equation which comes up in number theory and algebraic geometry that looks like this. Y squared is x cubed plus ax plus b. And this defines, if you consider it over the complex numbers, it defines what's called an elliptic curve. And this elliptic curve has some really interesting properties, but to see these properties completely, you have to look at this curve in projective space, and so you have to increase the dimension by 1 because, of course, so you're wanting to replace all the points by lines, and there is a projectivization method which can be made sense of, but in kind of abstract terms. But to transform this equation, to be a projective one, all you have to do is just upgrade all of the terms in this, all the monomials in this polynomial equation, so that they're the same degree. So I'm just going to put a z. Now it looks very artificial, but I'm just making all these terms match up in degree, and it turns out that then this defines a projective curve. One reason for doing that is that it gives you access to a point that you wouldn't have otherwise. So this has a solution, and I'm going to put the coordinates in what's called homogeneous coordinate form, which we'll come to, but it basically means you can that you take all these things up to scaling. So this point with y being equal to 1 and x and z, or any multiple even, and x and z being equal to 0, you can now see satisfies this equation. And if you do that, people sort of draw pictures. It's very difficult to draw a complex curve because like this, because even if you just look at the sort of solutions here, we want to look at complex solutions, and I'm only going to be able to draw real pictures here, but somehow this kind of picture is enough to see the features. It has this strange property, the elliptic curve, that you can add points together, and you do it in a kind of very geometric way. If I want to add these 2 points together, what I do is I draw a line between them, and one can show that it hits the curve at exactly one other point, like this. So you get this algebraic property that you can add points together, and gives it what's called the structure of an abelian variety. But it's very important that you do this in this projective setting, because then this point turns out to act as an identity element. So whenever you add this point to anything, you get back the point that you had to start with. Right, so what's true about elliptic curves is that you can use them by sort of adding points over and over again. You can in effect scramble data, and knowing how many of those points you've added is sort of a private piece of information that you can use as a cryptography key. So elliptic curves, which, as I say, have to be understood in this projective context, give you a way of encrypting data. And elliptic curve cryptography is actually the basis behind Bitcoin. So if you've heard of the blockchain and Bitcoin, then it's this setup which underlies all that stuff. Okay, so yes, projective geometry is worth studying. So let's define what we mean by projective space.